Let us look at some sets: set of natural numbers, set of alphabets, set of continents in the world, whole number that is not a natural number, number which is neither prime nor composite, set of solutions of equation x squared minus 1 is equal to 0, where x is a real number. Did you notice that each set has a different number of elements? This leads to categorization of sets on the basis of the number of elements in them. Let's explore how sets are categorized on the basis of the number of elements. We can categorize sets on the basis of the number of elements in them. The first categorization is finite and infinite sets. If the set has a definite number of elements, then it is finite. Otherwise, it is infinite. So, from among the sets we saw in the beginning, the set of natural numbers is infinite, whereas all others are finite sets. Let's consider some more sets and categorize them as finite or infinite. Consider these sets: the set of stars in the Milky Way galaxy, the set of molecules in a glass of water. Are these sets finite or infinite? Since the number of elements in the sets is too large to count, these sets may seem infinite, but actually they are finite. Notice that a group that cannot be counted is not necessarily infinite. Similarly, the set of men or women at a particular time on the earth is finite, though it is difficult to count them. However, the set of natural numbers is infinite. Let us prove it. We shall prove this by contradiction. Suppose that the set of natural numbers is finite. Then we must have a greatest natural number. Let's call it n. Well then, what is n plus 1? It must also be a natural number, given the property of natural numbers that every number has a successor and must therefore belong to this set. We have a contradiction here, as n plus 1 is greater than n. This contradiction arises because of the assumption that natural numbers are finite. This means that the set of natural numbers is infinite. What about the set of points on a line segment? Is it finite or infinite? That is also an infinite set, as the number of points between the ends of a segment is not definite. You may be wondering, then what is infinite? How large must be a set to be called infinite? To understand this, consider this illustration. Suppose there is a single grain of wheat. It does not comprise a heap, nor do 2 or 3 or 4 or 10 grains of wheat. However, at some point, the collection of grains becomes large enough to be called a heap. But there is apparently no definite point where this occurs. This is called a Sorites paradox. The name Sorites is derived from the Greek word soros, which means pile or heap. Similarly, there is no definite point beyond which we can declare that something is infinite. We loosely say that something is infinitely large. The concept of infinity was first given by British mathematician John Wallis in the year 1655. Let us now move further into the categorization of sets on the basis of the number of elements in them. We have seen that both finite and infinite sets have elements in them. These sets are called non-empty sets. But is it possible to define a set which has no elements? The answer is yes. A set which has no elements in it is called an empty set or a null set. We denote this set which has no elements in it by the Greek letter phi. We also write this set as a pair of curly braces containing no elements in it. And guess what? This set is as meaningful as the number 0. Its importance is not to be underestimated. Some examples of empty sets are a set X such that x plus x equals x and x is a natural number, as 2x equals x is not possible. Another example of a null set is set X such that x squared equals 9 and x is even. It is null because the number 3, whose square equals 9, is not an even number. Similarly, the set of girls in a boys' school is an empty set. What about the set with the element 0 in it? Is it empty? Note that the set with the element 0 in it is not an empty set, as there is one element in it. In fact, a set having only one element is called a singleton set. For example, the set of solutions of the equation x plus 5 equals 0 is also a singleton set. The number of elements in a set is known as its cardinality. It is denoted by n brackets the name of the set. For example, n brackets A denotes the cardinality of set A. For example, if A is a set with elements 1, 2, 3 in it, then its cardinality is 3. Let's look at some sets and write their cardinality. In the first case, there are 7 distinct letters, so the cardinality of that set is 7. Next, the cardinality of set B, in which the only element is 10, is 1. The set C has 6 elements, so its cardinality is 6. And the set D has 2 elements, so its cardinality is 2.